4, A being 1 indicates that my expression for A is clearly incorrect because we see this display here and the display is low active, meaning that A would need to be 0 in order to light up. In binary this is 3, A needs to be lit up. We add this A1 not into the expression in order to narrow down the outputs, but also this appropriately includes that A being 0 result, and we add this A1 not, this becomes 0 instead of 1. In assignment number 13, question number 1, I didn't adequately talk about some of the things I had to talk about, such as these things I'm going to add right here. So since the impedance across the capacitor is proportional to the impedance of the capacitor is proportional to 1 over omega, the angular frequency, the impedance of the capacitor will decrease as the frequency increases, and meaning the bulb will get brighter as the impedance decreases, and that's an important relationship to account for. In B, without a resistor, most of the voltage drop occurs inside the function generator since the resistance to the function generator is much greater than the resistance to the bulb. But by adding a resistor to the circuit, we make more of the voltage drop in the actual circuit, and this voltage drop decreases the current significantly, which prevents the bulb from lighting. In question number 2, I made a bad assumption here, and I did not need to make, and I'm going to talk about question 3 on this page as well. We have voltage here, and the complex conjugate changes the sign of the imaginary. And when we have this expression here, and we have these terms, and we combine them like this, we can use Euler's identity to change this expression to v naught squared z cosine of theta minus v naught squared over z I sine of theta. And when you take the real part of that, you're left with v naught squared over z cosine of theta times 1/2 gives you the average power. In question number 3, the total impedance is radical 40 ohms, and this allows us to find the total current. When we find the total current, we apply it respectively to find the peak voltages, which are 2.5 volts and 7.6 volts. In question number 4, I falsely assume these are negligible values because I didn't account for units, and when I account for the picofarads and the millihenries, which are the capacitance and inductor units, I add these factors of 10 to account for those, and those terms clearly become not negligible. The only real term being the resistance right here, the following 3 being imaginary. We get negative 2000J, 6000J, and 2000J, giving us a final equivalent impedance of 4 kiloohms plus 6000J kiloohms. In assignment number 24, question number 2 and 3, I didn't really talk about current as much as I should have, and I was speaking more in terms of voltage drops, so I revised my answers to talk more about current flow in the circuits. So for the AND gate, when we have one high input, there will be current will be completely restricted in that branch because no voltage can drop across that diode. So that forces all the current to come through here, and voltage will drop across the resistor and the diode, and there won't be enough current in F to or enough voltage in F in order to make a high output. When both of the inputs are low, all of the current is forced into these branches, and no current will be in F, also giving you a low input because these voltage drops here are really pushing the current in this way, and it will prevent any current from going into F. And then the opposite of that would be too high inputs, which completely restricts current in these branches because no voltage drops can occur across the diodes, so all the current is forced through F, and that gives you a high output of greater than 2.5 volts. And while the AND gate is all about restricting current, the NOT gate is very similar in that way. Now I'm going to talk about the current flow. So if you have a high input in A, then all of the current is just forced straight to the ground. None of it will go to F. Nothing will go into A because no voltage drop can occur. It goes straight down. When the input of A is low, we get a possible voltage drop across this resistor, which allows current to flow in this circuit, and F will be high. Thank you.